This lecture introduces the essential journey from analog waves to digital bits. Every modern communication system, from mobile phones to online video, depends on converting natural, continuous signals into a precise digital form. In the next slides, we will walk through the key stages of this transformation and understand why it forms the foundation of today's connected world. Analog signals exist in continuous time with infinite detail, representing physical phenomena such as sound and light. Digital signals, in contrast, operate in discrete steps using only zeros and ones. To enable computers and communication systems to process real-world information, we must translate analog behavior into digital form. This conversion creates a common language shared across all digital technologies. This slide outlines the digital bridge, a structured pathway that converts analog information into a digital bitstream. The process involves three primary steps: sampling, quantization, and encoding. After conversion, the data is transmitted and later reconstructed at the receiver. This model forms the standard architecture of digital communication systems worldwide. Sampling captures the value of an analog waveform at discrete time intervals. Instead of recording an infinite number of points, we take rapid snapshots that preserve the signal's behavior over time. The result is a discrete time sequence, often represented as a pulse-amplitude modulated signal. Sampling is the first step in digitizing continuous information. To accurately reconstruct the original signal, the sampling frequency must be at least twice the highest frequency contained in the analog signal. This requirement is known as the Nyquist rate. If the rule is not met, information will be lost. For example, CD audio uses a 44.1 kHz sampling rate to fully capture human auditory frequencies. When sampling is too slow, aliasing occurs. High-frequency components of the original signal appear as false, lower-frequency distortions in the sampled data. Once aliasing is introduced, it cannot be removed. To prevent this, systems follow the Nyquist rule and use anti-aliasing filters to eliminate frequencies that could corrupt the sampled signal. After sampling, each discrete time value must be mapped to a finite set of amplitude levels. This process is known as quantization. Because real amplitudes are continuous, quantization rounds each sample to the nearest available level. Although this enables digital representation, it introduces an unavoidable approximation of the original signal. The difference between the true amplitude and its quantized value is called quantization error. When combined across samples, this error manifests as quantization noise. The magnitude of this noise depends on the number of quantization levels used. More levels reduce distortion and produce a more faithful representation of the analog signal. Higher quantization levels give better signal fidelity but require more bits per sample, increasing storage and bandwidth requirements. Lower levels reduce file size but also reduce signal quality. Designers must balance quality and efficiency based on system needs, whether for high-definition audio or low-power sensor networks. In the encoding stage, each quantized value is assigned a unique binary code. This method is called Pulse-Code Modulation. If there are L quantization levels, each sample requires log base 2 of L bits. The output is a digital bitstream composed entirely of zeros and ones, ready for transmission or storage in digital systems. This example illustrates the complete conversion from an analog voltage signal to a digital bitstream. The waveform is sampled, the samples are quantized to one of 8 levels, and each level is encoded using a 3-bit binary word. Together, these steps demonstrate how continuous information becomes discrete digital data. Uniform quantization uses evenly spaced amplitude levels and is suitable for general-purpose signals. Non-uniform quantization allocates more levels where small values are common, improving efficiency for signals such as human speech. This approach enhances perceived quality without increasing the total number of bits. Once encoded, the bit stream is converted into voltage pulses for transmission across a physical channel. At the receiver, the pulses are detected and the digital data is reconstructed, reversing the entire conversion process. This forms the basis of baseband digital transmission systems used throughout modern communication networks. These principles underpin nearly every digital service today. High-definition media relies on high sampling rates. Mobile voice systems use non-uniform quantization to save bandwidth. Internet of Things devices use low-fidelity PCM to conserve power. Understanding this conversion explains how digital communication maintains quality, efficiency, and reliability. In summary, the digital bridge consists of three essential elements: sampling, which captures the signal in time; quantization, which maps amplitudes to discrete levels; and encoding, which converts these levels into binary words. Mastering this process is fundamental to understanding digital communication systems and the technology that drives our modern world.